Hello everyone, my name is Jorge Valderrama and I'm going to present my work that is about a machine learning based approach for uncertainty propagation and its application to launch vehicle design. The coupling of uncertainty propagation and multidisciplinary design, analysis and optimization, or MDAO, results in a large set of optimal trajectories and optimal vehicle characteristics. The multidisciplinary optimization of launch vehicles is computationally expensive as it includes a trajectory optimization that requires optimal control methods to solve. Coupling then multidisciplinary optimization inside a uncertainty propagation loop, it's a computational burden. You will see that we will focus on the output stochastic process. This is the set of optimal trajectories resulting from the uncertainty propagation. Here we can visualize the altitude profile as a function of the percentage of light. And then we aim to calculate quantiles and flight envelopes that are composed by upper and lower quantiles. Through my work to better visualize the results, I take the centered version of the stochastic process. This is that I subtract the median trajectory. In this case, like that, we obtain the central altitude. So three different approaches can be distinguished in the literature to perform the uncertainty quantification within an MDAO problem that contains optimal control. The first one is a nested approach, where a Monte Carlo simulation is used to obtain exact realizations of a code of MDAO plus optimal control. This easily becomes prohibitive due to computational cost. A second approach is an expander approach, where polynomial chaos are used to extend the optimization domain and solve a unique optimization problem. But this method is only efficient usually for 3 or less random input variables. The third method is the surrogate model approach. It consists of a limited size Monte Carlo simulation that is used to solve the MDAO plus optimal control and obtain a training set. Then a surrogate model is created using this training set, and then the surrogate model is exploded to create the output stochastic process. This method is faster than the nested approach and doesn't have any constraints on the number of input variables. Nevertheless, it has an intrinsic surrogate model error. So during my project, we looked to solve or to propose a solution for the error of the surrogate model approach. For this, we proposed an active learning methodology for quantile estimation of scalar field variables. It's important to notice that such a technique has not been proposed in the literature yet. So the methodology consists of creating an initial training set using a limited size Monte Carlo simulation and original code, then performing the Kahunen-Loew expansion over this output training set to reduce its dimensionality, and then the use of Gaussian processes to train and to predict for new outputs. Over these new outputs, a quantile is calculated and its uncertainty is assessed. If the uncertainty of the quantile is sufficient to our criteria, then we can say that the algorithm converges. Otherwise, we have to go through a refinement criteria optimization loop, where we look for the new samples that, when added to the training set, minimize the uncertainty on the estimated quantile. I'm going to show you some of the results for a mission of injecting a 10 tons payload into a 400-kilometer circular orbit, and to estimate the quantile of the 99% quantile of the altitude profile. It's important to notice that the confidence interval area represents the uncertainty on the estimated quantile. So here on the right, I showed the original training set composed of 200 trajectories. And to the left, you can see the estimated quantile over the outputs of the surrogate model. And in red, I show the confidence interval area representing the uncertainty on the estimated quantile. And the strategy looks to reduce this red area here. You will see that when the active learning methodology starts working, it starts to identify and add the samples that are close to the quantile of interest and effectively reduces the confidence interval area, hence reducing uncertainty. So we performed the experiment multiple times with multiple runs, and we represent the results within a a box plot to generalize the results. And we plot the evolution of the uncertainty, the confidence interval area, as a function of the enrichment iterations. So here you can notice that the iteration after iteration, the methodology effectively reduces uncertainty on the estimated quantile. And then we also calculated the error with respect to the validation set as a function of the enrichment iterations. And you can see that iteration after iteration, the active learning strategy effectively reduces the error with respect to the validation set. So in conclusion, an active learning technique for field variable quantile estimation was developed in a context of a multidisciplinary design analysis and optimization problem with optimal control. The technique reduces the confidence interval area related to the uncertainty on the estimation of the quantile, and also reduces the error with respect to the validation set. As future work, the technique could be extended to multidimensional fields to compute, for instance, quantiles on a pressure field over an aerodynamic surface. Thank you for your attention. These are some of the references that I used. Thank you.